Alright, alright, alright. Handling non-deterministic results. Superpose. Yeah, that would be the basic, one of the basic operators of programming in superposition, right? I have multiple things and I make them into sort of one thing that corresponds to multiple things or something. In previous tutorials, we saw that match along with any other function can return multiple non-deterministic as well as empty results. If you need to get a non-deterministic result explicitly, you use the superpose function, which turns a tuple into a non-deterministic result. It is a standard lib function that takes an expression and returns an atom. Okay. However, it is typically recommended to avoid using it. For example, is in the following program. Okay, so bin, I already have bin. If I evaluate bin, I get 0 and 1 as this is a superimposed result as a non-deterministic set of results. Now another function bin2 superpose takes expression 0, 1. Okay, so this is the same. Yeah, if I evaluate bin2, it's the same. It's a set of 0 and 1. Bin and bin2 do a similar job. However, bin is evaluated using one equality query. While bin2 requires additional evaluation of superpose. Yeah, it makes one equality query and then it expands into this expression. This needs to be evaluated. So there's another evaluation step. Okay, and that is aesthetically not pleasing to the meta programmer, I guess. Also, one may argue that bin is more modular and more suitable for meta programming and evaluation control. Yeah, I guess, yeah, the fact that I can query for bin and then I basically get these symbols or something. But here, if I query for bin2, I get this expression that is a function call again and so forth. Like, it's more complicated. Because here it is more, yeah, it's more modular, yeah. Because there are two elements of the same kind, but here there's one element with a nested kind of, there's two kinds of things, and here's one kind of thing, I guess. So it is more aesthetic. This is more aesthetic. That's true. One may want to use superpose to execute several operations. However, the order of execution is not guaranteed. And again, one can try thinking about writing multiple equalities for a function inside which superpose seems to be suitable. Yes, okay, so every time that you think you need superpose, maybe you just need multiple equalities instead, I guess. However, superpose can still be convenient in some cases. For example, one can pass non-deterministic expression to any function, both grounded and symbolic, built-in and custom, and get multiple results. In the following example, writing this would be inconvenient. Yeah, okay, yeah. Because otherwise I would sort of ad hoc say, the thing that I want to pass to this function is 3, 4, 5. Like if I do this with equalities, like I would need to write my input is 3 and like this 3, 4, 5 or something like that, and that is not convenient. Yeah, but something like this 3, 4, 5. Yeah, this is. I mean, this is like I'm a fan of programming in superposition. This is a great avenue that I want to explore. I think there's something so joyful about saying it's multiple things. I love the idea that you just say it's many things. It's not the one thing. It's many things. Yeah. And the beautiful thing about programming in superposition is it's sort of handled for you, right? This multiplicity is not something that you care about. It's something that is taken care for you because there's only one plus function, and plus just deals with single things, but it also deals with a multiplicity of things, right? So it's the evaluator that is handling this for me. Same way that Erlang is a language for parallelism and distributed systems or something, and I don't actually write code for distributed systems. I just write Erlang code. And the same way here, I write normal symbolic code, but it deals with the superposition of things, and that is what I find interesting. So basically, I don't think about superpositions. If I write programs that deal with superpositions, I'm not caring about superpositions. I pretend that the forest is a tree, right? I use the same function that I would use for a single element, but it also works for the forest. It works for the superposition the same way. So the code that you write looks as if you write for single elements, but it deals with more than one element as well, or with the superposition of elements. It's kind of something I discovered from thinking about programming in superpositions. Here, non-determinism works like a map over a set of elements. Okay. Another example where using superpose explicitly is useful for checking a set of non-deterministic results with assert equal. Yeah, we already saw that in the assert equal part. When both arguments still require evaluation, so assert equal to result is not convenient to apply. In the following example, we want to check that we didn't forget any equality for color. Yeah, sure. But we may need to be interested what exact value they are reduced to, whether IKB is reduced to international client blue. I'm gonna type this in. Okay, equal IKB becomes international client blue. Okay, then equal color green. Okay, then equal color yellow. Then equal color IKB. International client blue. It's kind of an alias for this thing. This is a color? International client blue. Synthetic ultramarine, similar to that is used in the okay. Oh, ultramarine. It's very, very, very blue. I feel like this is very blue. It's a deep blue hue, first mixed by the French. I don't know how to pronounce this guy. Yeah, something. IKB's visual impact comes from its heavy reliance on ultramarine, as well as clients' often thick and textured application of paint on canvas. This is ultramarine. Huh. Okay. Damn, this is a painting? That's nice. Yeah, this is a crazy color. Okay. So this is another color, international climb blue. Okay. Then we say assert equal match ampersand self equal. Now find all colors. Okay, this finds all colors. Including basically the symbol IKB, right? Yeah. No, wait, so yeah. Including the symbol IKB, and then if we evaluate this further, and it becomes this international climb blue. That's exactly the point. Yeah, that's exactly the difference. So if I evaluate this, I get international climb blue there, and not the expression IKB or something. Yeah, so if I call superpose, and then I basically call the functions, like I just write normal meta code that is a set of inputs. Yeah, okay, this is assert equal returns success. Then I say that's would be the other thing. If I say assert equal to result, now I have this problem. I can't do it in the same way because international climb blue is not the same as this expression. This is not evaluated, so it doesn't return success. Okay, so this is where superpose can be useful if I basically want to deal with a result set and I want this to be evaluated as well or something. Yeah, okay, well, yeah. I guess, yeah, you gotta. It's good to have this tutorial. So I saw, I guess, most of the language or something, at least in the pieces. Okay, empty. Empty. This is also a thing. Empty. As mentioned above, in MeTTa, functions can return empty results. This is a natural consequence of the evaluation semantics based on queries, which can find no matches. Yeah, so everything can return also nothing, no matches, empty, something empty. Sometimes we may want to force a function to return an empty result to abort a certain evaluation branch, or explicitly represent it to analyze this behavior on the meta level. I want to represent empty, I guess, sometimes. So that I see what is returning empty or something, I guess. Okay, so you can say superpose with an empty result list. If I evaluate this... what? Wait. This is a bug in my meta evaluator. I need dot. Dot. Okay, whatever. I'm just gonna say what's equal to the empty result here. Yeah. Okay, fixed. Now I can say I get this correctly. Okay, this is this empty result. Okay. Superpose nothing. The empty result set. Yeah, makes sense, I guess. You can also. I could. This would be valid to say that. Okay, but there's also empty. That's the same. Provide empty function to do the same in a clearer and stable way. Okay. Some versions may also use uppercase empty as a symbol to inform the interpreter about this. Yeah, I already saw this somewhere. What does something like this do? What? Wait 1 sec. Okay, you say equal foo uppercase empty, right? So if the evaluator is treating this special, then if I evaluate foo, it should return nothing, right? It should return the empty result. Yeah, okay. So it does, my implementation here does treat this uppercase symbol empty special, because if I say foo to empty 2, I have a different symbol here, and then I evaluate foo 2, I should get empty 2, of course. This is because it evaluates to this. But this thing is treated special. Okay. And this would be the uppercase empty symbol as a symbol to inform the interpreter about the empty result, which may differ on some level from calling a grounded function. Okay. This uppercase empty might also be different from calling the grounded function empty. Empty is supported more widely at the moment, so we use it here. Yeah, okay, well, this is a little bit of leaky abstraction for me as the user here right now. The fact that I need to worry about the different implementations, but yeah, I guess you don't get around these practicalities. Yeah, so the call a function empty could be used in the construction of asserts. Assert equal something empty. It could be useful in the construction of the asserts, but assert equal to result can also work. Wait, I'm gonna type what they say. Parent Bob and then exclamation mark. Assert equal match ampersand self parent Tom x. Quickly checking. That is nothing. Okay, this is just nothing. Empty. Okay, assert equal. That this is the same. Okay, this just says yes. Assert equal to result. That one doesn't evaluate the second argument. Okay, so this doesn't work. Missed result empty. Huh. Because it's expression empty. But if this is the empty result list here, that is allowed. Okay. Achso, okay. Okay. I see. Alright, okay. Yeah. Because with assert equal to result, I need to talk about the actual result list. I'm not allowed to put any symbol there and for it to work. But here, of course, I can do it because both arguments here are evaluated, and then they're both nothing. They're both the empty result list. As you can also see here, from the fact that this returns correct, that this returns success. So that's another use case, another use for empty. If I want to check that something doesn't return anything. But this, I can also use this. This looks actually a little bit cleaner, in my opinion. But yeah. Since expressions without suitable equalities remain unreduced in MeTTa, empty can be used to alter this behavior when desirable. E.g. equal EQ x true. Okay. Then evaluate EQAB. This doesn't reduce further because I said here that I need something with the same argument twice. Yeah. Okay, this is cool now. Yeah, this is cool. Yeah. This is cool. Yeah. This is cool. Because this returns the expression, but it would be cool if it would return nothing. And I can say it returns nothing by implementing another EQ expression, or how you call it, or another atom in the atom space, I guess. Where it says that EQ with two different things is empty, and now if I evaluate the same thing, I get the empty result, and that's kind of nice. This is nice. This is really nice. Yeah, it's also interesting that this is more useful than returning false or something. Actually, you can't return false. You cannot implement this in terms of false, because then this one, it will also still be false. Like if you would do this here with false with the second implementation, then EQAB, this is good. This would be false, right? This would be EQ2 AB, this I think would be false. Yeah, so this would look good. But the problem is that AA would be both true and false, yeah. Because AA is both the same variable twice and two different variables, sort of in a in a sort of like empty way, kind of. X and Y are also A, and A is also the same as X and Y. Unifies with X and Y. It's just that X is A and Y is A. So yeah. But this is where empty helps us. This is interesting. Yeah, it's like this time it first went here and said this is nothing. So no. It does. Why does this work? What is actually the difference? Here I say EQ AB false, yeah. So yeah, but here you kind of this empty is really special, because you kind of say that the moment your branch of execution, your query, finds this empty, this moment this whole branch is kind of thrown away. And that's the difference. Because here I don't ever go into... am I true about this? Am I right about this? Oh, it's exactly the other way around. It's kind of like saying, yeah, this branch of query is returning empty, but all the other branches are still allowed to return something, so that EQ of AA is still allowed to return true, and just the other branch... wait, what? So this other branch just doesn't contribute to the result. It just doesn't contribute to the result. But here in this version it does contribute. It would contribute false, which is not what we want. Yeah. Okay. Well, this empty thing is kind of central almost. I feel like you really need to understand that one, I guess. Okay, I'll keep that in mind, this empty one. Empty can be used to turn a total function such as if or unify into a partial function. So yeah, because some branches would return something and some other branches would not return something. When we have no behavior for the else branch, we don't want the expression to remain unreduced. Yeah. For example, you have an if statement, and then you say that I want to say that this is just nothing. I want to say that some expression is not just unreduced, but actually doesn't result in anything. Let us know that there is some convention in how the interpreter processes empty results. If the result of match for equality query is empty, the interpreter doesn't reduce the given expression. If the result of match for equality query is empty. Okay, I'm looking for like this here. I say empty, yeah. Then what does the interpreter do? It doesn't reduce the expression. It transforms the empty result of such queries to not reducible. But if a grounded function returns the empty result, it is treated as partial. When a grounded function application is not reduced, for example, I have this expression, because the function returns not the empty result, but not reducible. Okay, a function can also return not reducible, and then something that's not reduced. But this is only for grounded functions. This behavior may be refined in the future, but the possibility to have both types of behavior, a partial function is not reduced and evaluation continues, or it returns no result stopping further evaluation, will be supported. Yeah, okay, but I guess I have to see this in the wild. But okay, I see there are different things, different types of behaviors. Either you reduce an expression or you say that the expression, that you say that there's no result, and then it's the further evaluation is stopped. I understand this. I understand how to implement this version, so I'm already happy about this. Okay, from non-deterministic viewpoint, empty removes an evaluation branch. Yeah, it does that, yeah. If you consider all the results as a collection, empty can be used for its filtering, yeah. Yeah, it says filter, it removes it. In the following program, color and fruit produces non-deterministic collections of colors and fruits correspondingly, while filter prefer is a partially defined ID function, which can be used to filter out these collections. Okay, so partially defined is basically the opposite of total, so that you have all kinds of inputs, but in your output domain some are missing or something like that, or like, which is partial function. Partial function is that for some inputs you don't have an output, right? Partial function can be surjective, injective. This is not injective because some elements have the same output. A partial function f from a set x to a set y is a function from a subset s of x, possibly the whole x itself, to y. Okay, the subset s is that of the domain of f viewed as a function is called the domain of definition or natural domain of f. Okay, so I define a subset S of the domain, and I call that the domain of definition or the natural domain of f. S. if s is equal to x, then I have a total function. If f is defined on every element in x, then f is said to be a total function. So a total function is a subset of a is the special case of a partial function where s is equal to x. So the complete domain is basically the input domain. The domain of definition, S. Yeah, okay. Cool, I just learned. Well, yeah. So here I say that X is kind of not in S. So filter prefer has the domain of the set of blue, banana, mango. Yeah. That's its natural domain. That's for sure. That's the natural domain. Blue, banana, and mango, S. But I'm not entirely sure what X is. X is all possible inputs to filter prefer, which is, I guess that's all meta expressions or something like that. Yeah, okay. But yeah, it's partial because filter prefer doesn't take any input. It only takes a subset of inputs, blue, banana, and mango, and this is basically okay. This makes it partial, I guess. Yeah, I'm semi-happy with understanding it, so I'm gonna go further here. Okay, put this into my database. So there's some colors, there's some fruit. Now I define a function called filter prefer on blue, on banana, on mango, yeah. And for everything else, empty. So this is like saying that the user of the function, or the function is basically the preference function of our AI or something. It says that it likes blue, banana, and mango, and nothing else. And nothing else. So if I filter prefer a color, then I get the subset of colors that I prefer. It's like filtering. It's like saying color is all the colors, and then filter prefer only unifies, I guess, or finds an equality. Well, it finds equalities for blue and banana. For what are colors? Blue, only for blue. And then everything else, all the other colors are matched, are kind of catched with this X. But in this evaluation branch, it's empty, so that is removed from the result list, or it's removed from the complete evaluation branch. I guess prevents further evaluation, I suppose, because actually the outcome of filter prefer is sort of the small set of only blue. Okay, and if I filter prefer fruit, I get these, of course. In case of recursion, empty can prune branches which don't satisfy some conditions. Yeah, so that sounds very useful. That's interesting. Yeah, there was already an example somewhere. No, this is here we did that. So here we said empty. If that, so yeah, because you had all possible solutions, but you don't want to return all possible solutions or something like that. You want to say that only the solution where only the solutions that matter are interesting. So you say that the rest is just nothing. So yeah, it's kind of like there are certain things you need to do in relational programming that are maybe that are at first counterintuitive, but like I need to express certain concepts like empty results or something like that. Like this is like in procedural programming, you would find the solution and then return a solution or something like that. But this is not the case here, because the solution is already defined as the space of possible solutions, and I need to narrow down the solutions. It's yeah, something like that. It's like this NT is like cutting down in the calculation space of the program, kind of saying which branches are not explored further, so to say, or something like that, I guess. Kind of philosophically speaking, I guess. Okay, now, next. That was NT. Okay, NT was like super important, I feel like. But yeah, superpose was important because we're talking about non-deterministic evaluation. Then MT to cut down on the branches and make functions partial, so that basically things are not evaluated further and things are not just unreduced. That's the difference, because you can be unreduced or you can be nothing or you can be NT, and these two things need to be two different things in this paradigm. Yeah, because everything are the expressions that are being queried. So you match and query with everything, and then that either says that there are no results, or that says that you have an expression that is not reduced further, and that both of these things can sometimes be useful. So that's why we need something like NT to say which one of those we care about. Because otherwise, filter prefer two, right? This is now, I guess this is also a partial function, I guess. No, wait. This is a total function, but it's like, it has a different semantic. So this is actually a total function. So if I put hurdur here and evaluate, I get the expression filter prefer to hurdur. So you see it's a total function because all expressions go into this function and there's something coming out. Yeah, and then filter prefer blue, of course. This is blue. Yeah, and that's the difference. So this filter prefer number 2 is a total function. And it just has a different semantic. It says that I don't reduce it further, but I still sort of deal with the result of this. Like, there is a result for Hürde. But with filter prefer, it says that there is no result. This is something else. This is different. That's a difference somehow. Okay, now collapse. This is, I guess, the second in the non-deterministic evaluation kind of thing. The one that makes the symmetry complete, I suppose. Okay, I'm not sure what extreme element is. I don't know what extreme element. That's like the large. Maybe this is like the max or something. This is, for example, the max maybe of multiple or something. That would actually make sense. Because there I also actually do need to look at all the elements. Something like that, maybe, yeah. Or just the count, yeah. Then you also need all elements, yeah. So you need at some point sometimes to collapse the world, yeah. If you, for example, need to look at all outcomes and make a decision, make some next evaluation that takes all outcomes as inputs, then I need to collapse the world. Kind of fascinating concept here now. To me, this is fascinating. Yes, okay. Or more generally fold over them. Then I need the complete list. I need the complete list and return a single result that takes all of them into account. Yeah, that is, we may need to collect the results in one evaluation branch. Yeah, okay, so reverse operation to superpose is collapse. Ah, okay. It's just the reverse operation to superpose. So superpose takes a set of expressions and returns a result set, a non-deterministic result set, which is like, I guess, a special type kind of for the evaluator or something. Yeah, it's special because it's not a list or something that would be a list of values that is treated as one branch of evaluation. But the outcome of superpose is this non-deterministic result set that must be something that is treated as many values suitable for many calculations in parallel. I guess parallel is not the right thing to say because that's taken by computing, parallel computing. But it's a superimposed set. So everything that is superimposed, these are basically non-deterministic branches, and they don't see each other. Yeah. Okay. They actually never said this, but yeah, this is basically a non-deterministic result set. Like this concept, non-deterministic result set, wasn't really talked about, but it's the outcome of the superpose function. Okay, and now basically the opposite of this is the collapse function. So basically, I should get a list of things. So I say color are these three things. Actually, I have even more things defined. Yeah, color is this non-deterministic result set, or all these branches. And now I collapse it, and I get a single list. Yes, a single result with this list. Yeah, okay. It converts a non-deterministic result, that's what I call this, okay, into a tuple. Yeah, there's a single tuple, okay. Collapse is a grounded function which runs the interpreter on the given atom and wraps it, and wraps the returned results into an expression. Yeah, okay. If I run this, I get this. Here we've got a non-deterministic result. So these are three results from the color function and converted into a tuple that is a single result tuple with three elements. Okay, now make more colors. Collapse the color. Okay, let x be the collapse of color. Okay, so it's a tuple of a bunch of colors. Now superpose. Okay, this is the same. This is just the reverse. Okay. This makes the result list again. Prints with the square brackets. Okay, if I say superpose 1, 2, 3, it is a result list of 1, 2, 3. If I say collapse on the outcome of this, I get the tuple 1, 2, 3 again, of course. Tuple 1, 2, 3. If I say let x superpose 1, 2, 3. Okay, so there's multiple things. X is multiple things. Collapse this. Oh yeah, okay. This is now different. This is different. It did it 3 times. Okay. Wait, why is this different from this version? Because here's a single collapse call. Okay. Yeah, because... Okay, this has to do with the fact that the type of collapse is... if I say get type... Yeah, it's atom. Yeah, okay. So collapse doesn't actually... it's not actually a function where the argument is evaluated. I think that's the reason why this is actually different here. So collapse. If collapse sees a non-deterministic result, then it collapses it to a tuple. But if you call collapse 3 times because you have 3 evaluation branches, then of course it just collapses 3 times. So in each evaluation branch it made one. And if I say let x superpose something, I get a non-deterministic result, and then the body of let is evaluated non-deterministically. I guess this must work like that, otherwise these two things would not be different. Interesting. Okay, this is I guess this is also important to know, yeah. Like there might be a bug where you think, wait, why is this not collapsed? But if you evaluate collapse in multiple branches, then of course you also have multiple things happening, yeah. You need to call collapse in a single branch for it to do anything on a non-deterministic result, of course, so forth. The color function gives the non-deterministic result. Yes. The order of colors may vary, of course, yeah. The collapse function converts it into a tuple: green, yellow, red. And finally, the superpose function in let converts a tuple back. This is here to a non-deterministic result. The order of colors may change again due to non-determinism. Yeah, I saw that flipping around all the time anyway already. Not flipping, it's not, I think now it's deterministic. No matter how often I evaluate this, it's deterministic. Per run, kind of, but across interpreters, apparently, it's non-deterministic. The order is not deterministic, but the outcome is deterministic. And after, in the same evaluation context, it's deterministic again, basically, the ordering. Either way, this is just as an aside. Okay, so collapsing the color, that is a list now, a single list, single tuple. Then here I collapse color, call superpose in it, and I get a non-deterministic result again. Note that we cannot collapse inside superpose. You cannot collapse inside superpose. This wouldn't work. Okay, wait, this wouldn't work without the let. What would that be? That would be the superposition of collapse color. Wait. What the fuck? Does this make sense? It returns collapse and then all the colors. What? What? I'm confused. Because collapse will not be executed before passing to superpose. It will not be executed. Because superpose is evaluating all its branches, I suppose. So, well, this doesn't make any sense. I understand right now why this doesn't make any sense, because if I say I say superpose 1, 2, 3, this is the superposition of 1, 2, 3. If I say foo here, I get foo, right? And the same thing, if I say collapse, I just get the symbol collapse. Collapse 1, 2, 3, right? That is yeah, this is obviously not what I want. And this doesn't help if you add another paren, because now I get the superposition of this. So it's just a single element collapse 1, 2, 3, 4. So this looks confusing unless you understand what I mean. Actually, you get an error. So because it tries to it tries to evaluate this. Ah, okay. This also this that makes even less sense. Okay. But yeah, this is also super confusing because it's the symbol collapse. Yeah, and then the rest of stuff. That's the colors. Okay. That's how it works. That's good to know. This kind of like splices the color list into this list just as an aside. It's basically the splice list. Collapse will not be executed before passing the superpose. Yeah, and will be considered as part of the input tuple. In contrary, we cannot call superpose outside collapse. Because it will cause collapse to be called separately for each non-deterministic branch. This is this version. This is this version. I can say collapse superpose. That worked because collapse saw non-deterministic result list, I guess. But here the evaluator splits the world for me, I think. So collapse is called separately for each non-deterministic branch produced by superpose instead of collecting these branches inside collapse. Yeah, okay. So these are a little bit, I guess, the tricky the concepts to know about as you wouldn't be able to program correctly MeTTa. So yeah, this is important to know. Alright, working with spaces. Space API. Okay, I already know add atom. Space is adding atoms, then removing atoms is also a thing. Okay. New space is a thing. Creating tokens. Bind. You can also bind something in a space. Okay, just a little bit like a namespace, actually, enclosure with symbols that it can be bound. I guess creating tokens is a little bit like making a symbol and turning a symbol or something. And then imports. Okay, that imports a space. This imports a space. Okay. The spaces are the same the mechanism for modules, I guess. It would make sense. Okay, working with spaces, space API. Spaces can have different implementations, but should satisfy a certain API. This API includes pattern matching or unification functionality. Match is a stdlib function which calls a corresponding API function of the given space, which can be different from the program space. Yeah. Okay. Yeah. So I can also sort of build a subspace a little bit, maybe as sort of like a class definition or something like that, I guess. Or as sort of a database. Something like that. Oh, yeah, something like that. Okay, let us recap that the type of match is arrow, hyperon, space, atom undefined. Yeah, this is the match, yeah. So you see that there's this complicated type here. The first argument is a space, or more precisely, a grounded atom referring to a space. It needs to be a grounded atom. It needs to point to some subsymbolic data that is a space, that is implementing a space protocol somehow, satisfying the space API. The second argument is the input pattern to be unified with expressions in the space, and the third argument is the output pattern, which is instantiated for every found match. Match can produce any number of results, starting with 0, which are treated non-deterministically. Yeah, so 0 or more results. That is the outcome of match. The basic use of match was already covered before, while its use with custom spaces will be described in other tutorials, since these spaces are not part of the stdlib. However, the space API includes additional components which are utilized by the stdlib functions such as add atom and remove atom. Okay, adding atoms. the content of spaces can be found can be not only defined statically in MeTTa scripts. Here, this is the stuff that I type. When I type foobar, I added this to the space, but I don't need to type foobar. I can also call the function add atom, but can also be modified at runtime by programs residing in the same or other spaces. The function add atoms adds an atom into the space. Its type is its type is this type. Evaluate. So space, atom, and then the unit type. That is, I think, I went through this tutorial, but I don't have a video for that part. Yeah, this is basically the type that is the unit type that is for side effect functions, basically. The result type. The first argument is an atom referring to some space, to which an atom provided as the second argument will be added. Since the type of the second atom is atom, the added atom is added without reduction. Okay. In the following program, add foo eq is a function which adds an equality for foo to the program space whenever it's called. Then it is checked that the expressions are added to the space without reduction. Okay, I'm typing. Add foo eq is a function that takes an atom and returns a unit type. So the same type signature as add atom. Then we implement add foo eq $x. Now we say add atom to the self space. And what I add is that foo is equal to this x. So I add a foo equality to this space. If I say foo, that does nothing because I don't have an x. If I say foo plus 1, 2, yeah, okay. Now, wait, this is wrong. Not foo, what? I wanted to say add foo eq, okay. So now this adds to the space that foo is equal to plus 1, 2. And that is also evaluated. Yeah, so 3. This becomes 3, right? Oh no, wait, I say atom here. That's important. So it's not evaluated, and this says plus 1, 2. So if I say that, it says okay. And then something else, 3, 4. Now I say foo, and actually it basically looks up this and it finds these two expressions and then evaluates them. So I get to 7 and 3. Yeah, if I would match, yeah, that's the thing. If you would, you can still query the atom space and you would see that I didn't add 3 and 7 as equalities. I added these expressions. Yeah, so I can query for foo $x, find everything that is equal to this foo. Yeah, quoted, so it's not evaluated. Yeah, exactly. The x. Yeah, so now I see what actually is in the atom space, and that is that there's 3, 4, 1, 2, and then quote empty. I guess that was. Where did this come from? That is probably from somewhere earlier. Yeah. If it is desirable to add a reduced atom without additional wrappers, add foo eq but without atom type for the argument, then add reduct can be used. They also have implemented this already. Okay. This add reduct. Yeah. Okay. Yeah. Okay. And this actually evaluates that. Yeah, so you wonder a little bit why don't they just implement basically the opposite of quote, kind of? like exclamation mark. Why can I not write exclamation? Like, why can I not write this? Why can I not write add atom? I need to evaluate it, of course. Say something like foo, and here plus 10, 20. Yeah, this adds the atom to the atom space. Why can I not do something like this, that I say an exclamation mark here? That's how I would do it in Lisp or something. I would think that something like this would be possible. Yeah, in Lisp I would have here. In Lisp I would have a quasi quote here, and then I would say that I evaluate that part. That would look like that. But here they have implemented this add reduct for me. So yeah, then you can say here something, some code. But yeah, actually, okay, so you can do that, evaluate that. Oh, 2 times? Wait, 2 times? I don't know. This would look like this. Now I search for, okay, I'm gonna use here another, I'm gonna say bar here. Okay, now I look for bar and I get 30. Okay. Also, if I look in the complete space for the quality, for what is actually in the space, we'll see that there's actually a reduced version of 30. Yeah. Add reduct. And it's kind of, it's anyway sort of just convenience, because you can also, you could have done this anyway like that as well. So if I do this, yeah, bar, if I say bar 2, $x, this would also work. That's kind of this point about the expressions and the let, that this would also be useful. This would be the same thing. This is the same thing as saying add reduct. Maybe this is even more powerful. I guess this one is more, you can go one further, right? Say here something like this, and then here you have multiple things now. I guess this would have been hard to do with add reduct. I'm not entirely sure. Yeah, would it? Okay, let's query for bar 2, 15, 16, and 15. And if I try to do the same thing with add reduct, I'm gonna say bar 3 here, and now here I have something like 10 plus 5 and 11 plus 5. What does this do? Okay, this just works. Okay, I guess it just works. Okay, it just works the same. Okay, this was just the same thing, I guess. 15, 16. Okay. Okay, so arguably this is kind of less code